We're going to get to our next speaker. Short introduction because he will show very cool things. I'm just going to say it's going to be a great talk. Adrian Lara Moreno, please give him a very big hand. Have fun.
Thank you. Good evening, everybody, and thanks for joining my talk, maybe that late in the evening. I know it might be a little bit tired, but I hope that hopefully it will be worth it for all of you. I'm going to talk about how to successfully build and program sound field control systems. My name is Adrian, and I'm the head of research in Holoblood. I've been in the company since already more than 10 years, so there's plenty of much that we can tell you about. I would probably not be wrong by assuming a bunch of people in the audience area have had some kind of music making experience or do actually make music. So music making is an exciting creative process where pretty much there are no boundaries set. I would like to distinguish two separate processes in the stage of making music, not strictly independent from each other, but not always really properly interconnected. Those would be the music production and the music reproduction. In the music production phase is where creativity plays the biggest role and where artists take the leap in adopting and driving innovation. Synthesizers and samplers did revolutionize the way music is being produced and expanded the creative capabilities of many artists in ways they could not imagine before. New software-driven digital signal processing, filters, or effects also introduce new, unique ways of personalize your production. Some artists even made themselves some style or a signature that they are well known and recognized for. One example of them would be Daft Punk with the use of the effect of vocoder. Traditional music creation using instruments, it's also constantly finding new ways of evolving and combining new instruments. And finally, there are many different ways of interacting with music and triggering sound using very uncommon objects, such as, for example, the steps on a staircase, or use sound actually as a stimulus for other effects, such as video, lights, and many others. One great example of interacting with many different, of sound interacting with many different materials, that would be from the video clip of Nigel Stanford called Music versus Science, which I really recommend you to take a look at. Now that we got our production ready, we surely want to reproduce it and show it to the world, right? There are plenty of different reproduction systems that you can use for that. Among the most common ones, you can find mono systems, stereo, surround, or even Atmos or ambisonics in state-of-the-art projects. The biggest disadvantage of these kind of systems is that even when correctly deployed, they only deliver the desired experience to a very reduced number of people in the audience. That is also what is typically well known as the sweet spot. Very few people know actually where the music is going to end up being reproduced, and even fewer people take into consideration the sound system for the music production phase. Actually, the chances of your music production being properly experienced as you might have conceived it in the production phase are quite low, which actually brings me to my next questions and more or less the topic of my talk, which is, what if the loudspeaker system would take part in your creative music making process? I would like to introduce you to sound field control systems, particularly those with 3D capabilities, as it is the case of Holoblood, which we are hopefully will get to experience today as well. The idea of using an array of speakers to shape sound using beamforming has been around for many years, but until now it has been very difficult to achieve and to put into practice both for the horizontal and vertical axis simultaneously. Beamforming is a technique that implies the usage of multiple loudspeakers and interference between them, and they would put many of these speakers in the form of an array, a line array, or a matrix array in case that it would be like a two-dimensional speaker surface. They also are commonly driven by a digital signal stage, but I will talk more about this a little bit later. With beamforming, one can control the size, shape, and direction of the sound field of the loudspeaker. But before getting a little bit more into detail of how beamforming speaker systems function, I would like to introduce you to a couple of acoustical theoretical principles that would help you understand how these systems work. To understand how a loudspeaker can interfere with another one when they are built in the line array, let's first take a look at what the radiation pattern of the loudspeaker looks like. Let's have a look at the radiation of a single cone loudspeaker. We will take the example of a 4-inch loudspeaker or driver or transducer, as I would use any of those terms for the same purpose, which is loudspeakers. At low frequencies, the wavelength of sound is way larger than the size of the driver. So the resulting sound field from the transducer at the low frequencies will be spreading out evenly in all directions with the same level. At mid frequencies, when the wavelength that we are reproducing is more or less the same size of the driver that we're using to reproduce sound, you will hear louder sound in front of the loudspeaker, and if you move sideways, the sound level will decrease a little bit. At high frequencies, when the wavefront is much smaller than the wavelength that we are reproducing, at high frequencies, when the wavelength is way smaller than the loudspeaker, the radiation pattern will look as it's shown in the picture, which is it will be quite having a very rapidly level decrease if you move from the on-axis different position from the loudspeaker. Now, the relationship between the wavelength and the frequency is given by the following formula, where lambda equal c divided by f, where lambda is the wavelength that we are reproducing, c would be the speed of sound, typically having values of 340 meters per second, and f would be the frequency equivalent from that wavelength as well. As a summary from this slide, one could say that the loudspeaker radiates have a directivity pattern that looks differently for all different frequencies. As a consequence, the beam or the sound field or the coverage for that loudspeaker will look differently depending on the direction where you are actually listening to that loudspeaker. If you would be, for example, on axis, like listening right in front of the loudspeaker, you will hear all frequencies with more or less the same level. But if you will move sideways, you will find out like having, or you will experience different levels between the low frequencies and the high frequencies. Now that we know how a loudspeaker radiates sound at different frequencies, let's take a look at the interference of two sound waves, mostly when they are both overlapping with each other. So interference is a phenomenon that describes when two waves overlap with each other and they form another wave, which might have a louder, higher level or a lower amplitude level. Two waves of the same amplitude and frequency, which are in phase, interfere in a constructive manner, resulting in a wave of double of the amplitude. This is also known as constructive interference. When two waves are 180 degrees out of phase, they interfere in a destructive manner, and cancel each other completely, producing silence. This is also called as destructive interference. Advanced loudspeaker arrays rely on the principle of controlled interference that is based on the precise manipulation of phase between the loudspeakers built in the line array. A couple of slides before, remember we learned that a loudspeaker radiates differently for low, mid, and high frequencies. If we want to cause interference between several speakers in the array, we need to put them close enough so that the dispersion pattern overlaps physically and they can accordingly interfere with each other. To understand how wave interference occurs in space, let's take a look at a couple of examples using a monopole source. A monopole source is a theoretical, infinitely small sound source that radiates energy with equal level in all directions for all frequencies. The picture that I'm showing right now, it's the diagram, the activity diagram, or the radiation pattern of a monopole source, which from these pictures you can see on the top one, that would be the pressure level, where you can see the wavefront, which basically tell us how the wave travels across space and time. And if you would take that same information and take a look at the bottom diagram, that would be the equivalent level of that sound wave when it's being taken in a dB scale. That would be what is also known as an SPL map. Now, if you would place two sources with a distance of half of the wavelength that we want to control or that we want to interfere with, that would result in constructed interference in the front and the rear directions, whereas it will also cause destructive interference in the 90 degrees directions that would be on the left and right axis from the loudspeaker. Now, using 4 monopole sources, also distance half of the wavelength from each other, even more narrow radiation pattern will result in the front and back radiation. And in all the different directions, we will have like either constructed or destructive interference, depending on the angle where we are positioned. It's also important to know that the amplitude of the resulting narrower beam, if you look at the latest SPL map, it's louder than the original one from the monopole source, as we also learned in the constructed interference slide before. Now, the radiation pattern of an acoustic source is in a certain given plane, in this case, the horizontal plane. If we would cut a horizontal section of that group of loudspeakers, we will end up with what I'm showing in this plot here, which is called which is also called as the directivity diagram. In there, we can see many different components. The main one would be the main lobe, or the main beam, which is basically the lobe of energy containing the highest energy in all directions, typically shooting in the direction of interest, for example, the audience area. Grating and side lobes are beams with less energy that travel in undesired directions, and they are the result of spatial aliasing effects that typically happens when you position transducers too distant from each other, so they don't really properly interfere with each other in a constructive manner. The directivity diagram is widely used to represent the dispersion behavior of beam-forming loudspeakers. Now, line arrays combine the acoustical output from multiple speakers to obtain a narrow beam in the front direction of the line array. Sound field control using line arrays is achieved using many different techniques. For example, we could mechanically tilt the array so that the main lobe travels in a different direction, the direction where we want to cover the main audience area. Or alternatively, we could build many loudspeakers in that array with different sizes and dispersion patterns, and also tilt them mechanically with different angles so that they effectively cover a wide audience area. One example of this type of loudspeaker, probably you're already familiar with them, that would be these also commonly known as banana-shaped line arrays, or also J-shaped, that effectively combine the different loudspeakers mechanically tilted differently with different dispersion angles. Another approach to control the main lobe would be not using mechanical steering or mechanical tilting, but actually having still a flat line array and including a digital signal processing stage, also called as a DSP stage, in between the signal input and the line array that we're using to control the main beam. This principle is also known as digital beam steering, as obviously it involves a digital signal processing stage in this process. Now, if we zoom in into the required DSP, that would be just one example of what we can use. We could steer the main lobe to a given direction, in this case theta, by applying a delay to each of the loudspeakers built in the array. The delay for each loudspeaker channel can be calculated using the formula that I'm showing in the slide, which pretty much is dependent on the distance between the loudspeakers and the angle that we want the beam to be steered into. Now, as a result, if you look at the directivity diagram on the right-hand side, the main lobe is now formed to travel in the desired direction theta, which is defined from the on-axis angle of the line array. Since we are changing the radiation pattern by using controlled interference, that affects also the complete radiation pattern or the directivity diagram of the line array. So as a result, not only the main lobe is steered into the desired direction, but also the rest of the artifacts produced by this kind of beam steering are also moving into different directions. I'm talking precisely about the grating lobes, the rear lobe, and the side lobes. As you see also on the diagram, they are also accordingly steered depending on the steering angle. Now I would like to summarize and lay out the differences between different sound field control systems. But first, it's not really a proper sound field control system per se, but it's a loudspeaker, a point source. But nevertheless, I think it's worth to mention the behavior and the differences. So the first one that I'm introducing are point sources, which they do not actually offer any kind of sound control in space, other than the one where that is being decided during the design and manufacturing process of that specific point source speaker. Then we have digitally driven line arrays that offer the possibility to control the main lobe in the direction where the array is built in. In the example that I'm showing in the slide, the line array is built on the vertical direction, so as a result, the beam steering will be capable of being achieved in that direction. So we will be able to do beam forming in the vertical axis with this line array. And finally, many loudspeakers can be stacked not only vertically, but also horizontally, resulting in what is also called as a matrix array. Matrix arrays benefit from sound field control in the horizontal and vertical axis independently, resulting in full 3D control of the beam in all directions. Holoplot could be a unique example of a 3D sound field control system. Now I would like to mention a couple of considerations needed to understand the beam forming at different frequencies when using sound field control systems. The highest frequency control is defined by the driver spacing. Probably you might remember from the slide of the interference across space. As we learned previously, the control phase interference is possible when the distance between two loudspeakers enables the resulting directivity pattern to overlap physically. In that case, we need exactly to have at least half of the wavelength of the frequency that we want to control. In the directivity diagram that I'm showing on the top right-hand side, the full control of the main lobe is possible without any additional artifacts, and that would be possible as the example frequency that I'm visualizing would be below the frequency control of that specific matrix array design. On the other hand, on the bottom right-hand side, the example frequency would be above the frequency control of that matrix array. So as a result, we can control the main lobe into a different direction, but additionally we would get also some artifacts resulting from undersampling of the wavefront because of the distance from the loudspeakers would be too far for that frequency that we want to control. On the other hand, on the other side of the audio spectrum, on the low frequencies, because the wavelength is so large, we will need to have speakers spaced enough and sufficiently to be able to control that low frequencies. Specifically, again, that would be at least half of the wavelength. So that would be at least what we need to have our array built in. So the lowest frequency that we can control with matrix arrays could be given by the actual dimensions of the matrix array. In this case, since matrix arrays have two dimensions, the horizontal and the vertical, one could define separately the low frequency control in each of those axes. To give an example, and using the plot that I'm visualizing on the right-hand side, one could control the opening angle of the 100 Hz frequency beam and narrow it down to a 60-degree opening angle. So to achieve that, one would need an array of 4 meters width on the horizontal axis, and the other way around, if one would want to also control or like come up with the required length on the vertical axis, the same plot can be used. Next, I want to show you some features of 3D sound field control systems and how they can be used as a creative toolkit for your content creation. But before jumping into the creative side, I would like to mention some of the inherent benefits of 3D sound field control systems that put them actually in a very advantageous position when compared to other sound systems, such as obviously point sources or even line arrays. First, thanks to the beamforming capabilities, the horizontal and vertical axis independently, the dispersion pattern of the beam can be defined to precisely and optimally cover whatever audience area that the user can define. That would be the beam can adapt in terms of size, in terms of shape. And as an example, I'm showing the diagram for the SPL plot as well, resulting from a simulation of a matrix array on the right-hand side, where I wanted to show this one because this is particularly challenging as it is exactly doing the opposite as the nature of sound waves propagation would tell us, which is a typical sound source will spread with distance and will reduce level in that beamforming that we are visualizing on these plots. The beam is actually converging on the far distances, also increasing the level, and on the closer distances, the opening angle is quite open or quite wide, and the level has to be accordingly reduced. So this is, as I mentioned before, doing exactly the opposite as what it should be doing to be considered a loudspeaker. So because of that precision in delivering sound only where it's needed, the reflections from badly treated venues or spaces are minimized, resulting in an increase of the direct to reverberant ratio in that specific venue on that system. As a result, the speech intelligibility index will increase, delivering crystal clear messages to most of the audience area, even in very challenging acoustic venues. Just to quickly mention, the speech intelligibility index is a value between 0 and 1 that describes the quality of a specific system delivering a message in a specific venue. So obviously, the higher, the better. Finally, and directly resulting as well from the precise sound field control of our systems, the noise pollution can be greatly improved, meaning you could run shows with like either outdoor or inside the venue with less noise pollution, and you could even run multiple shows in parallel if those would be played at the frequency where the array can still control this frequency. Now, finally, let's take a look at how we can use Holoplot or any 3D sound field control system as a creative tool to enhance your show production with effects and features that you might not have ever thought about before. With Holoplot, you can configure multiple beams simultaneously from the same array, each with its own content, EQ, level, and shape. You can easily deliver content to various locations using beams with different properties. Some of the applications of this feature, for example, could be running a multilingual conference room by physically splitting the room into different beams with different languages. Another example would be delivering information around exhibits in a museum, or dividing or showing or delivering different beams into adjacent platforms in a train station. Holoplot sound field control algorithms are capable of tightly focusing audio content onto small groups of people, even down to individual members in the audience area. This is a unique and powerful tool for creating targeted sound experiences in the venue, experiences that actually change as you move across the audience area. So basically what you hear, what you will experience will depend on where you are. To be some examples that where we could use this feature, what we have done in the past is to recreate the virtual acoustics of a specific venue, for example, a church, and we have delivered like a single message to a single person in the audience area, that only that person would hear, and the rest of the people would hear just the acoustics of the venue. Another example would be that we have used quite often in trade shows. We had from our booth that was more or less in the middle of the space in the trade show, and we were like shooting a focused beamed or focused targeted area to the main entrance of the hall, and we were greeting and cheering up people to come to us as well. So this is indeed a great tool for sound designers, as it really creates truly novel experiences that were not possible before. Holoplot also develops and deploys wave synthesis algorithms. I didn't want to get much into detail in this presentation, but basically the array synthesizes also concave wavefronts that converge in one specific point in the audience area. As a result, the sound pressure level at that specific point is way louder than any other position in the audience area. That is also what we call focused virtual sources. Those focused virtual sources can be placed on the audience area, creating a proximity effect, something similar as if someone would speak to you at a close distance. But you can also place those focused virtual sources on walls or surfaces in the venue so that they reflect back to the audience area, something similar as if you would use a mirror to reflect light to a different direction. These targeted reflections are localized in the wall and not from the matrix array. So as a result, you can experience them as if they would be like one additional sound source or a loudspeaker that you can use for effects. So basically, even if you have a centralized systems, you could still deploy a fully immersive experience in the venue that you are deploying that system. All right, now that you know enough about sound field control systems and you might want to build your own prototype, one of your own. So this is what you might need for it. You need to get your hands both on the hardware and software development, since they both are dependent from each other and also a requirement. On the software end, you will need to implement the beamforming algorithms required to make the calculations that I described before. I mentioned before that very simple approach to do beam steering, but there are many more available in the literature and on the internet that are either more complex or adapted to matrix arrays as well. So before you have implemented or after you have implemented the beamforming algorithms, you might want to control them with the user interface. Some typical parameters might be, of course, opening angle or steering angle, and those will as a result trigger new calculations of the beamforming algorithms. Those resulting coefficients will be applied into the DSP stage, which is the one in charge of processing the audio input to the system. A good selection of DSP blocks that are required to do beamforming would be gain, delay, and filters such as FIRs or IIRs. Depending on the beamforming algorithm that you pick, you might need some of them or all of them. Now, of course, our purpose is not to process a single loudspeaker, but to actually build a sound field control system. So you're going to need multiple of those channels being processed in parallel, one for each of the loudspeaker built and mounted into your matrix array. And finally, each of those resulting coefficients from the algorithm will have an update into each of the DSP blocks whenever a change happens on the user interface, and also triggers a change of the coefficients required. Finally, we need to feed all the resulting channels from this DSP processing stage into the amplifier so that we can accordingly feed the signals into each of the speakers of the matrix array individually. And we need to have a multi-channel amplifier, as of course each of the signals is individual for each loudspeaker. Now, if we feel like building everything from scratch is too much, our friends from Hackaday have a nice project description for loudspeaker phased arrays. And of course, if you're not afraid of complexity, you can go beyond that and build the matrix array your own. Here are some old memories from our first prototype back in 2012. As you can see already, the complexity, it's quite large, and there's not even any electronics involved in there yet. Well, now that you understand how great sound field control systems are, you might want to know what is required to build your own system. But most importantly, I would like to give you as well an overview of all the complexity and the challenges that we had to overcome during the last years in our company. One of the main challenges is high count numbers. Everything at Holoplot is large. The number of loudspeakers, the computational power required for it, the number of supported audio modules, the IT infrastructure, the data being transferred, the number of audio channels being transferred, the number of bugs as well. Well, that one is actually a joke. One thing that we got quite used to in our system is to push the boundaries of every single component that is built in our system. Now I would like to give you a quick overview of the infrastructure that we have built. So first, of course, we need to have our matrix arrays, which are formed by stacking audio modules horizontally and vertically. The matrix arrays receive the configuration from the controllers using a redundant network. Also, the controllers are redundant, since this is one of the main requirements of our systems. They need to be robust, and they need to be having no single point of failure. The redundancy mechanism was, in this case, particularly challenging to build, because having two controllers only would not provide the majority of votes required to solve the latest status of the system in case something went wrong. The parameters of the system design and the ones required to achieve the array configuration come from a planning software, what we call Holoplot Plan, which can generate the projects required for the system, both in an online and offline mode. And finally, the audio source is coming from either a mixing desk or a digital audio workstation that speaks or can transmit audio over IP. Holoplot systems are designed to be decentralized and scalable. Our biggest installation and project so far, we have more than 2,000 audio modules in the same network. So delivering redundant data and audio to so many units in the same network is particularly challenging. And to give an example, many IP solutions that we had to fight for or that we were considering don't support more than 200 devices simultaneously. So this is like a large difference. And also something mentioning perhaps, which is interesting, is that what I've been showing here that we have come up in our system took over more than 3 years of a team of 20 full-time engineers to build, and of course this is not yet fully finished. Now I would like to zoom in into one of each of these components to give a little more of information and details. Holoplot Plan is in charge of configuring, optimizing, and simulating our matrix arrays. It builds online and offline functionalities, as I mentioned before, and it's built using protocol buffers over gRPC. That's a decision we pick because of the easy subscription mechanism, the backwards compatibility that it offers, and the efficient transmission that we can get from transmitting data into the controllers. It also builds a complex 3D environment that can do real-time simulation of our matrix arrays. And then again, remember, any kind of simulation using as many transducers that are built in our systems is, again, specifically particularly challenging. Now let's talk a little bit about the playback section of the system. We are also working on a software where we can control and render audio objects that are going to be reproduced in our system. But the biggest challenges come from sending the metadata of these audio objects in combination with the audio streams to all the modules in the system, and that they actually receive to each of the modules in a sample accuracy. So that's something that we're still working on. And this piece of software is also particularly interesting for show designers, as of today there is no even state-of-the-art plugins or softwares. The only thing they can deliver is to send or to render audio objects in any other system, but none of the specific features that our system can deliver. So that's also one of the tasks that we are currently trying to solve. Now about the controllers. The controllers are the core of all the Holoplot infrastructure. It is based on Yocto and takes care of sending and collecting information to the audio modules of our matrix arrays, providing also updates over the air, both for the own system of the controller, but also for the audio modules. It is written in Go and is built with many open source projects. Some of them we have even built our own, and they are of course released to the community as well. So you're free to check out our GitHub profile for that. And finally, as I already mentioned before, when it comes to the matrix arrays or the audio modules, the biggest challenge is in the audio modules comes from the high number of loudspeakers that we have built in there. In each of them, we have almost 100 loudspeakers per audio module. Each audio module needs to process up to 1.7 billion multiplications per second, something which is even challenging for many state-of-the-art DSP platforms. And of course, each audio module that we have done also implements many sensors and many properties that we can track in real time, such as the temperature and amplifier status, loudspeaker status, so a bunch of data that we capture from the module in real time and we send back to the controllers. And finally, speeding or wanting to speed the development of integrating third-party solutions is not always as efficient as anybody can think about. So we deal constantly with the boundaries and the limitations that these third-party solutions oppose to us, such as, for example, the available APIs that they deliver. They are specifically on the edge of what they can afford or what they can allow, and as we have like quite an extreme usage because of, again, the high number of loudspeakers. And finally, I wanted to also a quick overview about the testing challenge that we had. Something that we had to solve by, testing our system is quite challenging because we need to test the software, we need to test the hardware as we also develop it, and we need to test the integration from all of them. So we had to build or come up with that dedicated testing room, which is specially equipped with IT to automate the testing, the compilation, and the deployment of the new releases. And of course, as everything IT related, we also face the challenge that it doesn't matter how many deployments we test in-house, the clients and the users will actually end up always with something different that we haven't ever tested before, or any new device that interferes quickly with something else in the system. And last, as an overall conclusion for this presentation, greenfielding, which is what we did, is both great and challenging. So don't be surprised if you end up, or if you need to reinvent yourself across the way, since you're going to end up most certainly trapped in a corner quite often. However, greenfielding allows you to pick cutting-edge technologies that most of the times will actually make your life easier, more efficient, and indeed it will be more exciting. So now that's the end of my presentation. Now I want to show you those examples, now that you know as well the features that the system can do. Let's see how you guys react to it. So for that, I would like to, thank you. I would like to ask you guys to stand up. And I'm going to just play something that we have prepared, and let's see what happens.
Please turn yourself 90 degrees to the left, so your body faces the right side of the tent. To the count of 3, clap your hands to select the other half of the audience. 1, 2, 3.
So as you saw, because we were able to split the audience area into 2 halves, we were able to also deliver different messages, as I mentioned before, by providing different content. And yeah, we gave a different message to each of you. We're going to also show just a couple of other examples where we use the same functionality but with a different purpose. So we're going to show also from the multiple language, just a couple of languages for these audience areas. Feel free to move or change the audience area if you want, as you will also be able to experience the change when you move from one zone to the other one. Now, of course, you might think that this is easy because you have like 2 zones and 2 matrix arrays. So now we're going to do the same exercise. We're going to have 2 separate zones, but it's going to be coming only from one of those arrays. In this case, it's going to be the left array, which I assume is this one. Maybe that's the other way around. And we're also going to show some special effects that are being reproduced in each of these areas. But always remember, it's coming from one of the arrays. Then later on, I will change to the other array so that you can experience the same effect, but coming from different matrix arrays.
programmed it out of the left. Nothing's going to go, it's only from the left, not the left and right.
Ah, okay. True. Here's the next one. I made a mistake and it's always coming from this array, so that one is not programmed yet. He was the last one. Just a couple of more, just 5 more minutes. Is it playing? There you go.
We have 2 minutes in total. Then we have to cut up. So there's one question for demo tools are.
All right, time is out. So if someone wants to make any question, it's now the time. Or I have another demo for 3 focus points. So either we make a question or I show the demo.
Okay, let's
Either
do
way.
a vote. Who wants to ask a question? There's one who really wants. And who wants a demo or what? There's more people wanting the demo, but not that much. But I'll give the floor to you. The decision to you. You want to do the final demo? I think a lot of people are
Yeah,
standing,
let's do
they're
that.
curious. Let's do the demo. The question can come
We're
afterwards.
going to stay around and we can answer as many
Yeah.
questions
So
as you
do the
guys
final
want.
demo, because this is cool. Yeah.
So now we have 3 focus sources. You can find the crosses probably on the floor with neon duct tape. Look for them. They are somewhere in the middle of the audience area.
If I just can say, it's really cool to see so many people looking for sound, walking around and looking for sound. I've never done that before, but it's triggering lots of people.
Thank you, everybody. And if you're interested, then look for us. And as you know, of Passion here, we're also hiring. So if you're interested, also talk to us.
All right, ladies and
Thank you,
gentlemen.
everybody.
A very warm welcome for Adrian Lara Moreno. Thank you very much.